Welcome, students. Today, we're reviewing essential chemistry practicals and theoretical applications. This includes titration analysis, molar calculations, empirical reasoning, and simple qualitative analysis tests. Let's sharpen your understanding of how to interpret and analyze experimental data correctly. Imagine we're working with two prepared solutions. One is a dilute trioxonitrate 5 acid, and the other is a hydrated sodium carbonate solution. The acid is placed in a burette and carefully titrated into a known volume of the carbonate base in the conical flask, using methyl orange as an indicator. As acid is added, the color changes from yellow to orange, indicating the endpoint. The endpoint color is orange. I repeat, orange. From multiple trials, we record the initial and final burette readings to determine the volume of acid used. Averaging consistent titers ensures accurate calculations. The reaction between the acid and the sodium carbonate releases carbon dioxide and water. You'll recall that a mole ratio is involved, 2 moles of acid reacting with 1 mole of sodium carbonate, unknown number of hydration. Using this, we can calculate the relative molecular mass of sodium carbonate. For sodium, 23 times 2 is 46. For carbon, 12 times 1 is 12. For oxygen, 16 times 3 is 48. Now 46 plus 12 plus 48 is 106. That means 106 is the relative molecular mass of sodium trioxocarbonate 4. It has no unit. For water, the relative molecular mass is, for hydrogen, 1 times 2, which is 2. For oxygen, 16 times 1 gives 16. 2 plus 16 is 18. The relative molecular mass of sodium carbonate Y hydrate, water is 18, sodium trioxocarbonate is 106. So the value is 106 plus 18Y. For the nitric acid, hydrogen is 1 times 1 gives 1. Nitrogen is 14 times 1 gives 14. Oxygen is 16 times 3 gives 48. 1 plus 14 plus 48 gives 63. From the mass and molar mass, the molar concentration of each solution is determined. You may ask how. For instance, to calculate the acid concentration. If we have 3.65 grams of HNO3 in a 500 centimeters cube, the mass concentration will be mass in gram over volume in dm cube. The volume 500 centimeters cube divided by 1000 makes it 0.5 dm cube. That is 3.65 divided by 0.5, which is for A equals 6.3 grams per dm cube. The molar concentration will be mass concentration in gram per dm cube divided by molar mass, which is for A, 6.3 grams per dm cube, divided by 63 to yield 0.1 moles per dm cube. I hope you know where I got 63 from. Now we have the concentration in mole per dm cube for A. We know the mole ratio of acid to base to be 2 is to 1. Making Na to be 2, Nb to be 1, Ca to be 0.1 moles per dm cube, Va to be 26.45 centimeters cube. Vb is 25 centimeters cube of the pipette, Cb is unknown. From this formula, Cb is 0.05 moles per dm cube. You have to remember the connection between molar concentration and mass concentration, as you can see. Therefore, the mass concentration of solution B is 0.05 times 106 to yield 5.3 gram per dm cube. There is something more. If we have the mass concentration of the hydrated salt as 11 gram per dm cube. In your exam, this can be gotten from the second sentence, which is about solution B, something like, hydrated sodium trioxocarbonate 4 of 11 g in 1 decimeter cube. Something like this or more. The value of Y will be gotten as you by comparing the experimental volume of acid used with theoretical mole ratios, we can determine the degree of hydration, value of Y, in the salt. It's a simple comparison of mole-based reasoning. The value is approximately 6. That's how to solve for water of crystallization. You can also employ this method when working on percentage purity. Let's move to the analysis of an inorganic salt sample. Once dissolved in water, 3 separate tests are conducted. Test 1 using sodium hydroxide. Add aqueous sodium hydroxide dropwise, then in excess. A precipitate may form. Observe if it dissolves or remains. If a precipitate is formed, we have to state the color too. If white chalky, suggest Mg2+, Ca2+, Pb2+ ions are present. If gelatinous Al3+, Zn2+, Mg2+ ions are present. If blue, Cu2+ ions are present. If dirty green, Fe2+ ions are present. If brown, Fe3+ ions are present. Apart from aluminium, zinc and lead, in excess of aqueous sodium hydroxide which will dissolve, the rest remained insoluble. Test 2 using aqueous ammonia. Add aqueous ammonia similarly. Watch the solubility and color of any precipitate. If a precipitate is formed, we have to state the color too. If white chalky, suggest Pb2+ ions are present. If gelatinous Al3+, Zn2+, Mg2+ ions are present. If blue, Cu2+ ions are present. If dirty green, Fe2+ ions are present. If brown, Fe3+ ions are present. Apart from zinc and copper 2, in excess of aqueous ammonia which will dissolve, for copper 2, it forms a deep blue solution which is tetraamine copper 2 ions. The rest remained insoluble. Test 3. Add barium chloride, followed by dilute hydrochloric acid. A white precipitate that persists even after adding HCl may indicate a tetroxysulfate 6 ion presence. If the effervescent of pungent gas is evolved, it is trioxosulfate 4 ions. These observations help identify the presence of metallic cations and acidic anions like sulfate or carbonate. To distinguish unsaturated and saturated hydrocarbons, bromine water is used. An unsaturated compound like ethene will decolorize bromine water, while ethane will not. Another test. Use acidified potassium manganate, 7. It decolorizes in the presence of a double bond. To differentiate hydrogen chloride from sodium chloride, you could test with silver nitrate. In the presence of HCl, a white precipitate of silver chloride forms instantly. With NaCl, this also happens, but adding ammonia will dissolve NaCl's silver chloride precipitate, helping to tell them apart. Additionally, exposing hydrogen chloride gas to moist blue litmus turns it red, indicating its acidic nature. Always approach practical chemistry with confidence. Remember to record accurate readings, observe color changes keenly, and apply mole ratios effectively in calculations. Practice makes perfect. Review past titrations, test your understanding with balanced equations, and know your indicators. For qualitative analysis, always interpret your observations carefully using standard tests. Stay sharp, revise daily, and success will follow. Keep experimenting, chemistry is everywhere around you.